Students, hi, this is Mr. Bob. This video is about wind turbines, Wien's law, Stefan Boltzmann constant, and the solar constant. And so again, as usual, you have a choice whether you set up focus notes, do them by hand, or use an electronic version available there. The essential question is, what are the key concepts or some of the key concepts governing how energy arrives and flows within the Earth's system? And also just a reminder, I think it's important to pause this video when I ask sample questions and you try and answer it yourself, make your brain struggle a little bit before proceeding on with the video. So let's first start talking about wind turbines. And let's first start talking about wind. How does wind happen? If you look there, you have sun rays coming down on the Earth. And if we recall from earlier in the year, we learned that water has a very large specific heat capacity. So it's going to heat and cool pretty slowly, whereas in comparison, land is going to heat and cool pretty quickly. So what tends to happen here then is the heated land, the air above the heated land will become less dense and it'll rise. And in doing so, basically cooler air then fills in behind that lower pressure that's left behind, right? Because you have high pressure on the left, low pressure on the right, the air is going to move that way. And then the air behind that's going to fall. And notice what we get is we get kind of this sort of motion, this circular motion, or what we call a convection current. And oftentimes convection currents are basically the basis of wind. And so what we can do is we can use this wind, we can use the idea of a wind turbine to basically take the energy from the wind and make electricity. And let's look a little bit more about how that's done. If you look at any sort of wind turbine, the biggest thing you see are the rotor blades, right, and the big stand. But there's also a thing called nacelle. In that nacelle, there's a gearbox and a generator. In other words, what is happening inside the wind turbine is it's taking the kinetic energy of the wind and it's converting it into electrical energy. Okay, so the first big derivation I want to do with you is this, deriving the power equation for a wind turbine. And I have seen questions on IB where they ask you to do this, so it wouldn't be a bad idea to just be somewhat familiar with this. So one big assumption we're going to make for deriving this power equation is that the kinetic energy of the wind is completely converted into electrical energy by the generator. Okay, in other words, there's no energy degradation for the purpose of deriving this equation. So if you recall, the power equation is the rate of time of energy consumption. In other words, the change in energy over change in time. If you also recall, the kinetic energy of any object is 1/2 its mass times its speed squared. Okay, let's see how we're going to do it. So notice we have a certain radius for the blades, and that basically, when the wind turbine is spinning, that creates a certain sort of diameter of a circle or a certain area of a circle. And notice that wind is moving through the turbine. So the distance that it moves, the distance across the turbine that it moves, remember, just going back to kinematics, right? That can be thought of as speed times time, right? Because speed is change in distance over change in time. So if I take the change in time multiplied by the speed, I'll get the distance. So if I'm looking for the volume of the air, capital V volume, moving through the turbine blades at any one given time, that's going to be the area swept out by the blades times the distance traveled by a certain amount of air, right? Volume equals area times distance. So, but then we can substitute in this equation right here, in here, for distance, right? Speed times time equals distance. Okay. All right. So you see now we have an expression where volume equals area times speed times time. Okay. So now, how do I get the mass of the air? Because what I have to do is I have to basically figure out a way to substitute in to get an expression for this equation of mass. Well, density, which gets the symbol rho, equals what? Mass divided by volume, right? Or m over capital V. What if I solve that for mass? Notice I get mass equals density times volume. But wait a second. If you look up here, volume, I have this expression for volume, and I can just stick that in right here. Okay, and when I do that, I get a result that says that the mass of the wind moving through the turbine is equal to the density of the air times the area of the wind turbine times the speed at which the wind is moving times the time. Okay, now we're going to do one more thing that's going to help us bring this home. This right here can be substituted into this equation. And by the way, this kinetic energy equation can be substituted in over here for energy. So when I do that, let's watch what happens. Let's go down here. Power equals 1/2. Instead of mass, I'm going to put in the density times the area times the speed of the wind times the time. So that's my big mass term, which, let me just be really clear about that. That's that. Okay, and then I have speed squared divided by time. Okay, so notice I can clean this up just a little bit. Notice, let me actually, hold on, let me do this. I'm gonna think it's gonna get in the way, yeah. So to clean this up, notice the times cancel. And the speed squared times the speed is going to give me speed cubed. So that becomes, the result is that the power generated by a wind turbine is equal to 1/2 the density of the air moving through it times the area swept out by the blades times the speed of the wind cubed. And that's all I got. So notice what we have here is this equation. And when you look on your data booklet, that is actually listed in section subtopic 8.1. And that's a really important equation. I see that frequently used in IB world on exams and stuff. It's something I will definitely test you on. So it's something you're going to get some practice with and want to be able to do. Okay. Now, there are reasons why the actual power generated by a wind turbine will be less than that calculated by this equation. Okay. And you should know at least two of those reasons. The first one is that there is energy degradation within the turbine. Remember, that's one of those IB buzzwords, energy degradation. And it's an important one, right? Any sort of energy transformation has some sort of degradation involved. The second thing is, if you think about it, we assumed that we were going to use all the kinetic energy of the wind particles that are entering the wind turbine. Well, if we did that, when they exited, they would have no kinetic energy and the air would just stack up on the back side of the wind turbine, which isn't going to make sense, right? So the air molecules have to exit with some velocity. So the turbines can't use all of that kinetic energy, initial kinetic energy, which is an assumption we made when we made this equation. So know that this is an idealized equation, but there are reasons why the actual power output of a wind turbine will be less than what's put out, than what's suggested by this equation. Quick joke. Two wind turbines were standing in a field. One of them says to the other, "Hey, what kind of music do you like?" What did the second one say? "Well, you know, I'm a heavy metal fan." Yes, that's a good one. Okay, hydroelectric power is something we know pretty well here in the Pacific Northwest, and it's just important to take a second to understand how it works. So what you have is you have sun-driven evaporation rainfall, okay? In other words, the sun evaporates water from a low elevation, brings it up into the sky, forms clouds. The clouds move over to higher elevation, rain falls, okay? And so that water then is basically transported from a low elevation area to a higher elevation area. And so we can take advantage of that because when the water travels down the river, in certain places we have decided to back it up into a reservoir, and we've routed that at our time in choosing, we route that higher elevation water through a turbine. And it's the same idea as the wind in the sense that the turbine generates electricity on the other end. Right here, you can see a generator. So the kinetic energy, the transfer from potential to kinetic energy is routed through that wind turbine, causes the turbine to spin, and electricity is generated. Now, during times of less energy demand, you can use the excess electricity that's generated by this turbine to pump some of the water back up into the reservoir for later use. And that is something that hydroelectric dams do from time to time. This is something called pumped hydro storage or pumped storage scheme. Just a quick side note. This topic is the subject of considerable debate. Some leading scientists are basically have been arguing for the past few years about how much energy could be obtained by maximizing the strategy along with other things. Okay, one other area that I want to talk about here is about solar energy systems. And so when we talk about solar power, there are two ways we can talk about it. And when we're talking about solar power, we're talking about energy gotten directly from the sun's rays. So the two things we're going to talk about, we're going to talk about solar heating panels, and we're going to talk about photovoltaic cells. Okay, solar heating panels. What happens in a heating panel is something like this. You have some sort of insulation, and then on top of it, you have an absorbing sort of material, and then you route a liquid through it. And notice you route the liquid through it in a very sort of tortuous path so that it maximizes its time it's inside that material. And so let's say this is water, for example. And as you run the water through it, okay, sunlight's going to hit this panel, but it's going to be absorbed. And so what's going to happen is the cold water is going to come in here, but what's going to happen as it makes its way through this heat exchanger, the sunlight coming in is going to heat the water up. So by the time the water comes out of the pipe, you have hot water. This is like a solar water heater. Some of you may be familiar with this. Okay. And obviously, the slower the water or other suitable liquid is circulated, the hotter it can get. So that's how a solar heating panel works. In this case, what's happening is the solar energy is being basically converted to heat, and it's being transferred to an object that has that's colder and making it warmer, right? Heat is used to raise the temperature of the material, and most often that is a liquid. Now, this is different than a photovoltaic cell, which I want to talk about now. In a photovoltaic cell, what happens is the sunlight is directly converted into electricity. And you don't have to know all the inner workings. These things can get really complicated. There's things called p-n junctions, et cetera. But all you really need to know is that the photons, the incoming photons, knock electrons off of those atoms, and it causes a flow of electrons to be generated. And in this case, what's happening is solar energy is being converted directly into electrical energy. And notice that's a key difference compared to the heating panel. Okay, it's time to introduce a concept called black body radiation and to talk more about a concept called intensity. So let's first talk about color. If I say something is green, right, it can be green. Most likely it's green because when white light comes down on it, remember white is really light that has all different color components in it. That object absorbs all colors of the spectrum, of the visible spectrum, except for green. And so the green color is what hits our eyes. The green wavelength light is what hits our eyes, and that's what tells us it's the color green. Okay, so the key idea here is in physics, we have this concept of a black body radiators. And so a black body is an object that absorbs all wavelengths. And to be honest, all of us, to a certain extent, come close to, or to different extents, I should say, approximate a black body. So whenever you hear black body radiation, think of, in physics, we're talking about an idealized object that will absorb all the energy that is given to it, so it will look black, and it also will re-radiate all that energy, and hence we get the term black body radiation. And we can use this idea to kind of simulate what's going to happen here. One other idea I want to talk about is intensity. I don't recall if this is the first time I'm introducing this concept. I believe I've introduced it earlier this year, but intensity is the power generated per unit area. Okay, and it's going to be an important here concept for the rest of this unit. Intensity equals power over area. If you remember, power is SI unit for power is watts, and what's the SI unit for area? Meters squared. So the units, most common units for intensity are watts per meter squared. There's no like special unit for intensity. Okay, in black body radiation, let's see what happens here. Scientists have done experiments, okay? And so what they've done, and this was done a long time ago and repeated many times since then, if you take a solid, you like the sound effects, I hope you do, and heat it up, you can get it to glow different temperatures and glow different colors and that correspond to different temperatures, okay? And those colors will be in the visible range. This is, for example, let's say a metal. And so look here, Okay, here's what we're going to be plotting. We'll be plotting intensity versus wavelength. So wavelength is the wavelength of energy, the wavelength of electromagnetic waves coming from, being radiated from this object, okay? And the intensity is, again, the power per unit area at that specific wavelength. So that's what's being measured by the instrumentation in this experiment, okay? And scientists have done this a lot, and they've done it dating back to a long time ago. And so notice what happens here. The shape of the curve is what's really important, and what happens as we heat up the object. So if we heat up the object to a certain temperature, notice we get a curve that looks something like that. And then scientists kept heating it up and kept measuring the intensities at different wavelengths, and this is what they found. The curve shifts, as you can see there. Then they heated it up even some more, and notice the curve. So there are a couple of important observations to be made about this experiment. Notice I'm just noting there that you can see there's different wavelengths of light, and what you can see in the visible range is right there. So two big trends you want to make sure you understand about this. One is that the higher the temperature, the greater the intensity at all wavelengths, right? And that's pretty visible. The orange is higher than the red at all the different wavelengths, pretty much. Second is the higher the temperature, the smaller the wavelength of the maximum intensity. So this peak right here shifts. It shifts, and it shifts towards lower wavelength light. You can see that happening. Those are two important trends you want to make sure you understand. Okay, now there's a equation that's been developed, Wien's displacement law, and it tells us the wavelength of the maximum intensity. It tells us what this peak is and how it relates to the temperature of the object in Kelvin. And it's quite a simple equation. It basically says the maximum wavelength equals 2.90 times 10 to the negative 3 divided by the temperature. Okay, so we can use that, for example, to solve this scenario. And again, you should try and pause this video and solve it quickly on your calculator. The sun's surface has a temperature of 4,500 Kelvin. What is the prevalent wavelength of light coming from the sun? So to answer that, we would just apply Wien's law, 2.90 times 10 to the negative 3 divided by 4,500, and we would get 6.44 times 10 to the negative 7th meters. That is also 644 nanometers. If you look at 644 nanometers on the visible light spectrum, that comes in right here. You can see right here in the orangish sort of range of color of the spectrum. So that's why our sun most commonly or often can look orange to us. Now you're probably gonna say, well, the sun looks yellow, and that has to do more with the diffraction of the light as it comes through the atmosphere. But in terms of the most predominant wavelength of light that we see entering our atmosphere from the sun, it is orange. Okay, another important concept to be introduced here and to be used from here on forward is the Stefan Boltzmann law. So let's talk about it. This law basically says this: if I want to calculate the power generated by a radiating object, a black body or some other object, it doesn't have to be black body, it's going to depend on these four factors. And let's make sure we understand what each of these are. The sigma is basically called the Stefan Boltzmann constant, and that's a number right here, and it's the number that you have in your data booklet. And basically, like I said, this law shows the relationship between the temperature of a black body, because this is temperature in Kelvin, and the power emitted. Okay, so the E is something called emissivity. I'm going to have a slide on that here in a couple minutes. A black body emits as much power as it absorbs. Okay, that's an important thing to remember. And so the emissivity is going to be 1 for a black body. And this is important to know when solving problems. Oftentimes you'll see problems that say, assume the object is a black body, or it'll give you the emissivity. And then the important thing here, one of the important things about this equation is that we can manipulate it to get an expression for intensity. Now, if you remember, what was intensity? Intensity is the power per unit area. So notice what I can do with this equation here. If I divide both sides by area, then I can get that the power per area, or the intensity, equals the emissivity of the object multiplied by the Stefan Boltzmann constant multiplied by the temperature raised to the fourth power. Okay, and that is an important expression. It's not in your data booklet. This expression, this law is in your data booklet, but this formulation of, or reformulation of the law is an important one to remember or to be able to derive. Okay, so here let's do an example together. Mercury has a radius of 2.50 times 10 to the 6th meters. Its sunny side has a temperature of 400 degrees Celsius, and the shady side you can see there's much cooler temperature. Treating it like a black body, find its average power, use the average surface temperature. Okay, so to figure this out, we are going to have to use this equation up here. Whoops, no, didn't want to do that yet. Okay, the area of a sphere. What's the area of a sphere? If you don't remember off the top of your head, that is actually in your data booklet. It's like the first or second page. It is 4 pi r squared. So we can calculate that. 4 times pi times 2.50 times 10 to the 6th meters squared. So let's do that. 4 times pi times 2.5, 10 to the 6th squared, and I get 7.85 times 10 to the 13th meters squared. And for the temperature, we're going to use the average temperature. So that, whoops, come on, 673 plus 73 divided by 2. So what is that? 673 plus 73 equals, divided by 2 equals, that is 373 Kelvin. All right, so the average power put out by Mercury would be equal to this whole big equation. So let's just plug in the numbers. Emissivity said is 1. We're going to assume it's 1. The Stefan Boltzmann constant, 5.67 times 10 to the negative 8. The area is 7.85 times 10 to the 13th. And the temperature is 373 raised to the 4th power. So let's go ahead and 5.67, 10 to the negative 8 times 7.85, 10 to the 13th times 373 raised to the 4th power. And we get 8.62 times 10 to the 16th watts. So that's 8.62 times 10 to the 16th joules per second. Okay. Important thing to note is that since no body's at absolute zero, it follows that from the Stefan Boltzmann law, pretty much all bodies will radiate at some level, right? So you are powerful. Okay. All right, so this is really important. I want you to pay attention to this sort of little demonstration here. Intensity, the intensity of an object, let's say here's the radiator right here in the middle, the light source in this case. What happens to that intensity as it radiates outward? Well, notice if I am, say, 1 meter away from this light source, notice I have 1 square meter on each side, a little patch here. But let's say what happens to the same patch as the waves continue traveling out, and they're now 2 meters away. Well, 2 meters means that the area here of the power coming through is now not 1 square, but it's spread out over 4 squares, 2 squared. Okay, so notice what's going on here. The intensity of any power source goes down with increasing distance away from the source. So if it's doubled, if the distance away is doubled, then the light energy is spread out over 4 times the area. And if it's tripled, what's it going to be? You can see there it's going to be 9 squares. Okay, so this comes up, or this kind of exemplifies something called the inverse square law, and has to do with the surface area of the sphere. And this is important because what you need to realize is that the intensity is going to diminish over time and over distance. This is important for us here on Earth. Now we're gonna get there here in a moment. So here's the example. The sun radiates energy at 3.85 times 10 to the 26 watt. What is the rate at which energy from the sun reaches the earth per unit area if our orbital radius is 1.5 times 10 to the 11th meters? Okay, so to figure this out, here's the sun, okay? And whoa, do you see that it's radiating? Let me show you one more time. That's kind of the sun radiating out its energy. And here we are on the earth, okay? The earth, I'm just gonna draw, I'll do it in blue, will show up, won't it? Yes, the earth is here. And notice the earth is a certain, come on. The earth is a certain radius away from the sun. So this is the orbital radius here. Okay, and that's important. So to figure out the intensity, right? The intensity is the power per area. And remember, the power we can figure out using Stefan Boltzmann, so sigma E A, oh, excuse me, we didn't even have to go that route. Apologize, because we already know the power. So, so now we just have to figure out the area. So the power is 3.85 times 10 to the 26 watts. The area is 4 pi and r squared. In this case, the r is the orbital radius. So that's the distance that the energy has traveled. So this is 1.5 times 10 to the 11th meters squared. So that's 3.85, 11, yep, 26. Okay, so if you calculate that in your calculator, and I've done it already, you get an answer that is 1.36 times 10 to the third, not 103. Let's make sure we correct that. 10 to the third meter squared. That's what you would get. Watts per meter squared. Okay, so let's make sure we understand what that means. The sun radiates at the surface of the sun. If you were there, I wouldn't want to be there because you wouldn't be alive. It radiates at this power output, 3.85 times 10 to the 26 joules per second. But by the time that power reaches us here on Earth, it's been spread out, it's been diluted, right, over a hugely vast area. And so what we get, one square meter patch of surface on the Earth will get 1.36 times 10 to the third joules per second hitting it. That's what this is saying. So the question is, why is the solar intensity different at varying latitudes here on Earth? You probably may be aware of this, but this visual is supposed to help you do it. So if you look at it, okay, notice here's the sun, right? And the sun is coming and hitting, the sun's rays are coming and hitting the Earth. But notice, if it hits it at the equator, okay, you get something that looks like this. That's the area over which the intensity is being spread out, the power is being spread out. But if you're at a, let's say you're at a higher latitude, like let's say here in Portland, okay, notice it's bigger. And then if you're even at a higher latitude, notice it's even more big. And I'm not taking into account the curvature of the Earth, right? Or excuse me, not the curvature, but the tilt of the Earth. It's tilted, towards the sun, so that this also varies obviously depending on the time of the year. But the point here is this is spread out, and the figure I'm showing you is the average, okay, the 1360 watts per meter squared. By the way, that's on your data booklet at the bottom. It's called the solar constant. It's something that you have available to you there. Students forget that, so you might want to write that down. Okay, let's talk about emissivity. That is part of that Stefan Boltzmann equation, and we can talk a little bit more about it, okay? So it basically quantifies the emission absorption properties of a body compared to a black body of equal size. So how do we calculate the emissivity of an object? Well, basically what we do is we say, okay, we know a black body is a perfect emitter and absorber. In other words, it absorbs and then it re-emits all that radiation. So it has an emissivity of 1. So something like charcoal, for example, will have an emissivity pretty close to 1, 0.95, for example. So a body that can't emit or absorb any radiation is going to have an emissivity of 0. A mirror has it gets pretty close. You can see there it only has an emissivity of 0.05%. So what is the emissivity of a body? How do we calculate it? One way to calculate it is it's the ratio of the power emitted by that body compared to the power that would be emitted by a black body of the same size. So in other words, what we can say is the emissivity of a body, any material, is equal to the power that's being emitted by it divided by the power that a black body of same dimensions would emit. Okay, so E equals P body divided by Stefan Boltzmann constant times the surface area divided by the temperature, which is at raised to the fourth power. Let's talk about albedo. So when light strikes an object, some of it's going to be absorbed, but some of it's also going to be scattered. So if light strikes a mirror, nearly all of it will be scattered because it has a really low emissivity, meaning that mirror is going to scatter most of the incoming power that it receives. Okay, very little is going to heat up the mirror. But if light strikes a surface covered with, say, a paint like lamp black, nearly all of it's going to be absorbed. In other words, most of the incident power is going to be absorbed into that object. Very little of it's going to be scattered. Okay, now albedo is closely related to emissivity, and it's basically scattered power, the ratio of the scattered power to the incident power. So you can see there albedo equals P scattered over P incident. And again, it's just a ratio of the goes ins or the goes outs divided by the goes ins, if you want to think about it that way. Like I said, a mirror is going to have a very high albedo, okay, because it's going to scatter or reflect most of the incoming power, whereas a black body is going to have an albedo of almost 0. And therefore, what's going to happen? It's going to heat up, right? A black body is going to heat up much more so than a mirror because it's going to absorb a lot of that power. Why do we care about this? Well, first of all, one thing that IB doesn't talk about a lot, but it's an important, I think it's an easy expression or useful expression to keep in mind to keep track of this, is if you take the albedo of an object and you take the emissivity of an object, those two numbers should add up to 1. We're simplifying things a little bit here, but let's just stick with that. Okay, now if we look at the Earth's surface has a certain amount of albedo. And depending on, if you look here, there's some interesting things here. Depending on what is on the Earth's surface, the albedo of that part of the Earth's surface can vary quite a bit. Notice if we look at this, it varies by summer and winter, but let's just look at summer for a second. You can see here that there's a wide range here. Notice snow right here has a really high albedo. It doesn't absorb a lot of the energy that it receives. It reflects a good number of it, scatters a good number of it. On the opposite end, ocean water has a really low albedo. It'll absorb a lot of the energy that it receives, okay? Why is this important to us? Well, first of all, want to make sure you realize the reason it's important to us is because of what's going on with climate change. With climate change, one of the things that's happening is this has been happening for a long time, is the incoming rays of sun are being absorbed more and more by our atmosphere, and therefore it's causing much of the snow that used to be the snow and ice that used to have a high albedo, it would melt. When it melts, it turns into ocean water, which has a really low albedo. So it's unfortunately a positive feedback loop in the negatives, in the unfortunate sense for us, because what happens is you get a reinforcing feedback loop. As more of the snow melts, more of the energy is absorbed by the ocean water that replaces the snow. Therefore, it gets warmer. Therefore, we end up melting more of the snow, et cetera, and the planet gets warmer. So obviously, this is a pretty complex topic, and I'm simplifying it. But one little fact that IB seems to want you to know is that the Earth's mean yearly albedo, in other words, the average albedo of the entire surface of the Earth over the course of the year is about 30% or about 0.3. Okay, the actual albedo is going to depend on a lot of factors. Okay, so we're done. Hopefully you have a better understanding of the key concepts governing how energy arrives and flows within the Earth system. Thanks so much, everyone.